All right, welcome back to Etale Cohomology on October 27th, 2020. I hope everyone had a good weekend. So now that we're recording, any questions before we get back to talking about new stuff? All right, so just a brief reminder. So last time we finished talking about Etale pi 1. And we also introduced ZL sheaves and QL sheaves. And in good settings, so in the least setting, those were just the same as continuous pi 1 representations. So today I want to talk about a kind of grab bag of topics. And so this is our attempt to rapidly develop everything we need so that we can actually start proving the Weil conjectures. So I want to start with a discussion of smooth base change. So unfortunately, like proper base change, the proof of this is just too complicated to give in a course. I'm going to try to say a little bit about it later on in the course when we get to vanishing cycles. But the technique involved in the proof is it's really complicated. But let me at least state the theorem and tell you some applications. So here's the situation. So this is another base change theorem. So meaning another situation when the base change morphism is an isomorphism. So let me draw the usual diagram. So suppose I have x to s is some morphism pi. Then I have t to s, which is given by f, and then x prime is the base change. So this is x times t over s. And then the theorem is as follows. So suppose that that f is a constructible sheaf on x, and that f is smooth. Or well, first of all, so f the orders the orders of the stalks of f. These are finite groups. Have order invertible on the base. And f is smooth, this morphism f, not the sheaf f. Then there's a base change morphism, which goes from the pullback of the derived push forward of our sheaf f. And that goes to, let me give this a name, pi prime, and this is going to be f prime. That goes to the push forward of the pullback of f. And the statement is that this is an isomorphism. All right. So what this says is that if you no matter how bad this pi is, here I've stated this. We're going to apply this in some case where things are not quite varieties. But so here what's actually needed is that this is a finite type separated map. So what this says is that even if pi is quite bad, as long as you're pulling back along a smooth morphism, things are not so difficult. And this also so maybe a remark. So how do you actually apply this? So there are situations which are not quite smooth morphisms where this still applies. Namely, if f is a filtered limit of smooth morphism. So this still applies. And the sort of main situation, maybe I shouldn't say the main situation, but a very common situation where one applies this is when f is an inverse limit of smooth morphisms. So for example, like some kind of common examples are where e.g. like f is the inclusion of the generic point of a generic point, or a strict tensillization. Sorry, if I say strict tensillization, I guess I should say the fraction field of a strict tensillization. And that sort of thing. So for example, one consequence of this statement is that if say S is a variety, then cohomology always commutes with base change to the generic point. Okay, and maybe since I'm not going to say much about the proof, let me kind of say a little bit about the intuition. So what causes in topology, what causes cohomology to fail to commute with base change? So the way that happens is if let's say you're just base changing to a point. So the way cohomology can fail to commute with base change is if the cohomology of the fiber over your point is different from the cohomology of nearby fibers. So somehow the failure of cohomology to commute with base change measures that change in topology of fibers. So at least one thing you can think about is when you're pulling back to the generic point, at least, so this sort of very special case of the smooth base change theorem, is that the generic topology of a family of maps is always kind of constant, which I hope is at least reasonably intuitive. Like if you have a family, sort of changes in topology should happen in along closed subsets of the base. So this is the smooth base change theorem. So there's a non-trivial corollary of it, which maybe let me smooth. So this is called the smooth base change theorem. So there's a non-trivial corollary of it, which is called the smooth and proper base change theorem. Which I want to explain a little bit about because it's a good excuse to discuss cospecialization maps. Excuse me. Sorry, 1 second. Sorry, I have a little error in my notes. Let me quickly check something. Okay, yeah. So suppose that, so we have the same diagram as above. So suppose that now pi, sorry, now suppose pi is smooth and proper. Maybe I should recopy the diagram because you guys have no way of seeing what I've written in my notes here. So here's the diagram. So suppose pi is now smooth and proper. And again, we have this condition, f is constructible sheaf on X. With the orders of the stalks of f invertible on S. And moreover, suppose sorry, f should be LCC. Sorry, I really screwed up the way I've written this in my note. So so we have a smooth proper morphism, an LCC sheaf f on X, and we've assumed that the order of the stalks is invertible on S. Then the theorem is that that all the derived push forwards are in fact LCC. so again, this says that this is saying that well, we have cohomology commutes with base change because pi is proper, and this is saying that the cohomology of the fibers doesn't change. All right. So it's not obvious, by the way, how this follows from the smooth base change theorem, and it follows by applying it in this setting where we were base changing to the fraction fields of strict tensilizations. So let me make a couple remarks about this. So the remark, and this is a really, I want you guys to try to work out this exercise, which is find a counterexample if you drop the hypothesis on the order of the fibers. If you drop the hypothesis on the orders of the fibers. So meaning, let's say you're in characteristic P and F is the constant sheaf FP. So one can find examples like this, and you have enough information, at least treating, for example, the proper base change theorem as a black box to actually prove that your counterexample is a counterexample. So maybe let's actually pause for a second, and because I want to see how I want to make sure you guys are following. So can anyone suggest a place one might look for a counterexample where one drops this hypothesis that the order of the fibers is invertible on the base?
Sorry, may I ask the question?
Yeah, go ahead.
I can't see why this result should be related to the diagram.
Sorry. Yeah, there's no. Yeah, sorry. That was going to be later in the proof. Yeah, all you really need is pi here. Yeah. Sorry.
Okay, sure. Thanks.
Yeah. Yeah. So does anyone have any ideas about how to find a counterexample where one drops this hypothesis?
Maybe an order P cover of GM over a field of characteristic P? Or do you need something more complicated?
Why would that be a counterexample?
I don't know. I'm just throwing it out there.
Okay, so but you want to take like S to be GM and X to be.
Yeah.
Yeah. So I don't think a finite map can work.
Okay.
Because all you'll get is you'll just get the you'll get the FP to the degree. You'll get some local.
Oh, that's true. Yeah.
No, so it has to be some kind of not a finite map.
Okay.
Any other ideas? Okay, so maybe let me give you a hint. So hint is take a family of elliptic curves. Take a family of elliptic curves such that at least one fiber, such that let's say the generic fiber. So this is elliptic curves in a characteristic P. So this is over FP, say. Well, whatever. Let's just say over, yeah, in characteristic P. Such that the generic fiber is ordinary, but at least one fiber is supersingular. So for example, you would take the universal family of elliptic curves over some modular curve. And then take your sheaf F just to be the constant sheaf FP. So does anyone see why this will work? Why not all the derived push forwards will be LCC?
The rank of the cohomology jumps in the supersingular locus.
So yeah, so which cohomology and how does it jump?
It goes to 0 in the supersingular locus.
Yeah, so if you take R1 pi lower star of FP, well, okay, first of all, you need to use proper base change, right? So proper base change tells you that you can compute the the fibers of R1 pi lower star FP after base changing to a geometric point. And then as Sasha says, if you have a supersingular elliptic curve, well, we computed, well, in principle, we computed FP cohomology of such things because we wrote down a long exact sequence involving the Picard group. And if you compute what you get, you're going to get, sorry, that's not quite true. Sorry, let me think for a second just to check. Yeah, so sorry. So this is actually a little subtle, so you can't quite use the Picard group. So the claim is that R1 pi lower star of FP X bar is equal to FP if the corresponding elliptic curve, so the elliptic curve over this point, is ordinary, and 0 if it's supersingular. So I think the easiest way to do this is this is actually not so trivial. So what you can do is you can compute, so this thing is equal to H1 of EX bar FP by proper base change. So, and sorry, I shouldn't have said you can do it by relating it to PIC, because FP and mu P are different in characteristic P. But what you can do is you can relate it to the fundamental group. So this is, sorry, this is just HOM continuous by what we talked about, I think 2 class periods ago, from pi 1 E X bar into FP. Okay, and now this I claim is FP or 0, depending on what situation you're in, so ordinary or supersingular. Okay, and how does one check this? One needs to understand what is pi 1 of an elliptic curve. Okay, and then the underlying claim here, so is that pi 1 Etale of an elliptic curve is just the same as the total Tate module. So it's the product over all primes P of the Tate module. Okay, and then this is something where we know what it is for an elliptic curve. So in particular, the P part is either ZP or 0. Okay, so what is the content of this claim? I mean, ultimately, I'm going to leave it as an exercise, but what you should check is that what you need to do is write down the category of finite Etale covers of an elliptic curve. You would argue that they're all actually isogenies, so that all the objects are elliptic curves, at least if you're over an algebraically closed field. All the maps are isogenies, and then isogenies are classified by subgroups of, or by sets with an action of the Tate module. Great. Okay, so let me explain a kind of restatement of this theorem, which is useful and which kind of explains a little bit of functoriality of L-adic cohomology that we haven't really seen yet. So this is so earlier we saw a specialization map for pi 1. So now we're going to see a co-specialization map for cohomology. So yeah, so what's the situation here? So suppose that X is a scheme, and eta and Xi bar are geometric points of X. Of X. And here, suppose that eta bar specializes to Xi bar. Then I claim that there's a non-canonical specialization map, and we'll see what choices you need to make in a little bit. Specialization map from F Xi bar to F eta bar, where here F is any constructible sheaf. on X. All right. So I guess rather than writing proof, I'm going to write construction here. So can anyone help me make such a map? So these are, just a reminder, these are the stalks of F at our two geometric points. So maybe someone could start by reminding me how to just define these stalks. Any thoughts? So let's write down what is F of a geometric point C bar. Anyone? So it's some direct limit, right? So what is the direct limit taken over?
Just Etale opens containing C.
Yeah, so it's a little subtle because C bar is a geometric point, so it's U, and then it's not quite. It's like you have to pick up a lift of C bar to U, right? So you pick a geometric point of U bar that maps to C bar, and then you take F of U, right? And we want, so the dotted arrow means we don't have it yet. We want to map to F eta bar, which is the same thing. So the inverse limit, the direct limit rather, over VV, where these are Etale neighborhoods of eta bar of F of V. So how do we get a map like this? Any thoughts? So somehow we have to use that C is the specialization of eta.
I'm sorry, over there, are you saying we need to specify a geometric point lying over?
Yeah. So the definition of an Etale open neighborhood of a geometric point is it's a, sorry, I'm sorry about that. So it's an Etale open of X with a lift of our geometric point to that Etale open.
I see. Okay, thanks.
Yeah. So any thoughts? So the observation, and I think maybe Arvind was thinking about this given his question, is that so suppose I have one of these U's. So in particular, one feature of U is it's an Etale X scheme whose image contains C bar, right? Whose image contains like the physical point of X that C bar is mapping to. So what can you say about such a thing? So what does that imply, given that C bar is a specialization of eta bar? So if U maps to X and then C bar here lands in the image, so this factors through. So the statement is that, so at least part of the condition is that this factors through the image of U, right? So the image of U is an open subset of X, so it contains a point. What does that say about points generalizing to that point? Sorry, I'm in a very question and answering mood today, so I'm going to continue pausing until someone says something.
I think that eta bar is going to map into the image of, factor through the image of U.
Yeah, exactly right. So the fact that eta bar specializes to C bar implies that it also factors through the image of U. So what that means is that in the weak sense that the images of U, contain C bar, then they're like, that's some kind of weak notion of Etale neighborhood, namely without this U bar. So they're also, so these U's are also Etale neighborhoods of eta bar. right? So these Etale neighborhoods of C are also Etale neighborhoods of eta bar. So to make them actual Etale neighborhoods of eta bar, you would have to pick a geometric point. So you would actually want to pick. So you want to pick a lift like this, right? So let's just do that. So for each you pick a V and you lifting eta bar, so mapping to eta bar. Okay, so now we've turned each of these things into an Etale neighborhood of V. So this is the choice, right? Okay, and now given that, well, now what is an element of C bar? It's you know, of C bar, it's sections to these on sufficiently small Etale opens. So what that means is that we get sections we get elements of this on sufficiently small Etale opens, right? So in particular, once you make such a choice, well, you have to do this compatibly, and we'll see in a second that that's possible. Although it's really just formal from the fact that this is a filtered colimit. So once you make this choice, given a section here, you get a section here. So in other words, let me just say that very concretely. So if you have a element of the stock here, what is that? It's the germ of a section to F, right? And so that extends to a small open neighborhood of C bar, and eta bar is contained in any open neighborhood of C bar. So that's morally what's happening here. Okay, so explicitly, what choice are we making here? So what is the explicit choice? So what does this depend on? So this depends, I claim, on a choice of map OX C bar. So the strict tensillization at C to OX eta bar. Okay, and I claim, okay, so I claim that such a map picks out geometric points of each U over eta bar. That's a little exercise using the definition of these rings. But moreover, I claim this map. So what is this map? So this is literally the above construction applied to the sheaf to OX Etale. Okay, so this is what the choice depends on. Okay, so maybe let me just say a word about what, like in practice, what this actually means. So in practice, so suppose you have, so suppose R is a complete DVR. Say, well, let's just say R is a DVR, and X to spec R, let's call this pi, is a proper morphism. And let's suppose that, let's say little k is the residue field of R, and capital K is the fraction field. So what this gives you is, if you take Ri pi lower star, so if you take F to be Ri pi lower star of, let's say, the constant sheaf ZL, Z mod L, this is a constructible sheaf, and we can look at F at the close point, so that's K. So what is this? This is the cohomology of the fiber, because we have a proper map with Z mod L coefficients, and we can look at F the fiber over the generic point. So this, well, even if X wasn't proper, this would be the cohomology of the generic fiber. And we have a map like this. So in particular, viewing on this side, we get a map from the cohomology of the special fiber of our family to the cohomology of the generic fiber. So this is called a co-specialization map on Etale cohomology. Okay, and in topology, what does this mean? Well, it means what you're supposed to think is you have a family over a disk that the total space of that family is homotopy equivalent to the special fiber, and then you have an inclusion of a generic fiber. So what you're supposed to imagine is that this is actually the cohomology of the total space, which is the same as the cohomology of the generic fiber, and then pullback gives you a map to the cohomology of the generic fiber. So this is the Etale cohomological version of that. So in other words, if you have a cycle or a cocycle on the, if you have a cocycle on the central fiber of a family, you can spread it out to get a cocycle on the generic fiber. So that's what we've just constructed, is that kind of spreading out map. Great. Are there any questions about that? Okay, and then the proposition is that a constructible sheaf F satisfies the following. So it's LCC if and only if all co-specialization maps are isomorphisms. So this is a good exercise to test you understand the definition of the co-specialization maps. Are there any questions about that?
I'm a little worried about the reverse direction. If all the specialization maps are isomorphisms, is this necessary imply that it should be infinite?
I'm sorry?
As a stock of, I mean, if you have all the.
So constructible sheaves always.
Sure. Yeah, sure. Of course.
Yeah, so you have to use constructibility. Yeah. Does that help?
Yeah, sure.
Great. Yeah. Okay. So now let me state a corollary of this, which is sort of one of the very useful ways people use. So this is just really a restatement of the smooth and proper base change theorem. So suppose we're in the situation of the smooth and proper base change theorem. So pi x to s is smooth and proper, and F is an LCC sheaf on X Etale, such that the orders of the fibers, so such that orders of the stalks are invertible on S. So then, well, what did the smooth and proper base change theorem say? It said that the push forward was LCC. So that what this says is that, well, now we can so now given eta bar and xi bar geometric points of S with eta bar specializing to xi bar, we get that the co-specialization map, so the map HI x xi bar, let's say with coefficients in F restricted to x xi bar, we get this co-specialization map to HI x eta bar, F restricted to x eta bar is an isomorphism. Okay, so that's a sort of concrete way of understanding the smooth and proper base change theorem. So this is saying that the topology of the fibers of a smooth and proper family don't change. It's an analog of Erisman's theorem, if you'd like. All right, are there any questions about that? Okay, so let me just apply this to do some kind of computation. So the corollary is, so suppose that that we have, so let's suppose K is a a field of characteristic p bigger than 0, and suppose that x over k is a smooth proper variety. So then what this tells us is that we can, I'm going to state the theorem a little vaguely and then explain what I mean. So then if x lifts to characteristic 0, we can compute its cohomology. Let's say it's FL or ZL cohomology. Where here L is not equal to the characteristic of the ground field. Okay, so there's two things I need to explain. I need to explain what it means to lift to characteristic 0 and what it means, what can compute means, right? So let me explain those two things. So first of all, what does it mean to lift to characteristic 0? So can anyone, does anyone have any thoughts about that? I'm curious. So what you should imagine, by the way, is like what I mean is that I just want to directly apply this theorem, right? So I need to get myself in some situation where, where xk is the specialization of something in characteristic 0. So how do I do that?
I guess you can use a weak vector.
Yeah, exactly right. So you don't necessarily even need the Witt vectors, like a ramified extension of the Witt vectors is fine. So what you need is that, x, so what this means is that there exists a smooth proper let's say R scheme X over a DVR R such that the residue field of R is K. And sorry, I'm using a kind of curly K here, and such that X, the special fiber of this X, is isomorphic to the X we started with. Okay, so there's a little bit of subtlety here that I want to stress, which is that this X has to be a scheme. So it's not enough. So what deformation theory will typically give you is it will give you a formal scheme over the formal spectrum of this DVR. So the sort of example to be aware of is so when can you do this kind of thing? So the first thing you get is that if H2 of X with coefficients in its tangent sheaf is 0, you get a formal lift. So this, we discussed obstruction theory a little bit, or deformation obstruction theory in some very, very rapid way when we were talking about specialization maps for the fundamental group. And so there was this obstruction to lifting. And in the case of deforming schemes, the obstruction to lifting lives in this group. So if the group is 0, we can lift. And we get so what that gives us is it gives us a formal lift. So we lift, let's say you can take the Witt vectors of K and you can lift mod P and then P squared and P cubed and so on and so forth. And so that gives you an inverse system of schemes, but that doesn't actually give you a scheme over R. It just gives you an inverse system. If you take the inverse limit, you don't get a scheme, you get a formal scheme. So this is not enough. So what is enough? So what is enough is that if you can lift an ample line bundle. So if you can also lift an ample line bundle, also formally lift an ample line bundle, then formal Gaga implies there's a lift. So in particular, you win. So in particular, if X is projective, so it has an ample line bundle, H2 X Tx is 0, and H2 XOX is also 0, then you win. Okay, so why is that? Well, this group is the obstruction to lifting X, and then this group is the obstruction to lifting is the obstruction to lifting a line bundle, or deforming a line bundle in general. So this is so these are some criteria. So what this is saying is that in principle, the cohomology of a smooth projective variety in characteristic P satisfying these two fairly draconian conditions is computable. So I'll say in a second what I mean by computable. I don't just mean like formally computable. I mean like there's a fairly effective way to do it. But let me just give you some examples of schemes which lift in this sense, smooth projective schemes that lift in this sense. Does anyone actually have any examples that they like?
Your elliptic curve.
I'm sorry?
Your elliptic curve.
Yeah, so curves in general work. That's a, yeah. So curves, here are these obstructions. By curve, I mean smooth proper curve. So for curves, these obstructions are 0 because they're in H2, and curves have vanishing coherent H2. So abelian varieties also work. This is highly non-obvious. So for an abelian variety, this group is not 0, and this group is also not 0. But nonetheless, any abelian variety can be lifted to characteristic 0 with an ample line bundle. What's not true, and this is really, I think, awesome, is that a random lift doesn't work. So if you choose a random lift of an abelian variety to characteristic 0, it will typically not be algebraizable. So it typically won't have any line models on it whatsoever, except for the trivial bundle, or degree 0 bundles. So K3s also work. This is a theorem of Boolean. But the simplest situation is hypersurfaces and complete intersections in general. And complete intersections in general in Pn. So can anyone tell me why those lift to characteristic 0 in this sense?
Can you use like formal Gaga? Again?
Sorry, can you say that again?
I was wondering if you can use like formal Gaga.
Yeah, you could, but there's a very down to earth reason, which is that if you have a completed intersection, so it's just defined by a bunch of equations, right? And you can just pick lifts of the coefficients of the polynomials in those equations to the bit vectors. And then I claim that thing will still be a smooth proper complete intersection. And well, why is that? It's because all of those things are open conditions. All right, so what this is saying is that these are some examples of varieties where the procedure I'm about to describe will give you will let you compute their Etale homology. Are there any questions about why these examples fit into our paradigm of being liftable to characteristic 0?
Is this known for Calabi-Yau's in general, or is there some obstruction?
It's false.
Okay. Okay. Okay.
Yeah, it's not obvious. I mean, so what is true is that in characteristic 0, Calabi-Yau's are always unobstructed. That's called the Tian-Todorov theorem.
Mm-hmm.
But in characteristic P, it's false. Yeah, it's not. I mean, I guess what I would say is the reason why it's false and the failure to be true is reasonably well understood. So Stefan Schor has a bunch of papers about this. What is clear is that somehow the characteristic 0 proofs are not going to work. So there's an analytic proof, which obviously isn't going to work in characteristic P. And then there's a proof using the T1 lifting theorem, which I have a short write-up of on my website, which or the T1 lifting theorem itself only applies in characteristic 0. Great. Okay.
Yeah,
So
other questions. So abelian varieties, this H2 of the TX isn't vanishing, so you don't necessarily have formal lifts. Is
You do have formal lifts, but it's not formal.
Okay.
Yeah.
Are there examples where you do have formal lifts, but not necessarily formal lifts of ample line bundles, but nevertheless you have algebraization?
Basically, no. I mean, I think the only way we know how to algebraize formal schemes is with an ample line bundle.
Okay, great.
Yeah. Yeah. I mean, I think you like, in some sense, the answer is yes. Like, what you could take is you could take a non-projective variety over C. So such a thing will still admit a model over a finite type Z algebra. Then you could complete it a prime, and then you get a formal scheme whose generic fiber, which you created as the completion of some algebraic object with no ample line bundles on it. So yes, in some sense, that's an answer. But like,
okay,
but I think the real life question I think you're asking is like, is there another way to algebraize formal schemes? And the answer is like, as far as I know, no.
Okay, interesting. All right.
Yeah. Cool.
Maybe one more question.
Yeah.
Yeah, maybe I need is more or less a comment because I see Deline has proved we conjecture on K3 services. I'm always wondering why this is necessary. Does this have something to do with this lifting?
In some sense, yeah. So the reason, I mean, so I should say it wasn't, I mean, he proved it before proving the Bay conjectures in general. But it's not actually, it's not something you do on the way. It's sort of just a different thing.
Okay, so just a special things and
yeah.
not
So,
necessary.
but what's special about K3s and what makes them, what made Deline able to prove the Weil conjectures for them first was that they're closely related to abelian varieties. So essentially, you reduced the statement to K3s to the statement for abelian varieties, and that did use lifting. I mean, the proof uses lifting. I think, yeah, I guess it's necessary actually for the argument now that I think about it. But the sort of key input is that the cohomology of a K3 can always be found inside of cohomology of an abelian variety, and we knew it already at that point in the Weil conjectures for abelian varieties.
Okay, sure, thanks.
Yeah. Yeah. So, but the proof that that statement is true in positive characteristic does use lifting. Okay, so I've now explained what I mean by lifting. So now let me say what I mean by can compute cohomology. Okay, so by the smooth and proper base change theorem, it's enough to compute the cohomology of xk here, even k bar, where this is a lift, where here k is the fraction field of a DVR. So maybe I think I call this curly x. Where here k is the fraction field of a DVR to which x lifts in the sense above. Okay, so how do we do that? Well, here this is some variety over k bar. So it's defined by a finite collection of polynomials, and those polynomials have finite limiting coefficients. So in fact, what we can write is we can take Q, adjoin the coefficients of the polynomials defining x, so take an algebraic closure of that lives inside of k bar, and it also lives inside of the complex numbers. And you have to choose an embedding. So there's evidently a model of x over this field, right? So that there are two claims. So claim one is that the natural maps from x adjoining this weird field, x over this weird field. I mean, I'm just abusing notation and writing x for another model over this field. So well, this maps to sorry, other way around. Is mapped to this from xk bar, then also a map to this from XC. So claim 1 is that these maps induce isos on cohomology. And then claim 2 is that the cohomology of X base change to C is computable, or at least we have a lot more techniques to compute it. So 2, I think we've already explained more or less. So 2, this follows from the Arden comparison theorem. At least if you believe that singular cohomology is computable, we already know that for varieties over the complex numbers, Etale cohomology is the same as singular cohomology, at least with finite coefficients, or with ZL coefficients, which is a corollary. Okay, and there are a lot of ways of computing the cohomology of like complex manifolds, for example, like Morse theory is very effective. Or in general, like this is highly non-trivial, but any complex variety is homotopy equivalent to a finite CW complex, and then computing the cohomology of such a thing is not so bad. I mean, writing down a homotopy equivalence to a finite CW complex might not be so easy, but that's at least something, again, which you can do with, say, Morse theory. So can anyone tell me why is 1 true? So let me actually make one kind of a proposition. So suppose X over K is a variety where here K is algebraically closed. And then K subset L is an extension of algebraically closed fields. Then if F is a constructible sheaf on X, such that the orders of F, of the stops of F are invertible in K, then I claim that HI X Etale F to HI XL Etale F pulled back to XL is an isomorphism. So any thoughts? So I claim we can deduce this from something we stated earlier today. So I claim this follows from the smooth base change theorem. So in characteristic P, there's a little extra argument, but here, at least in this application, I'm in characteristic 0. So let me say what's happening there. So in characteristic 0, an extension of fields is a direct limit of smooth morphisms, right? Like separable field extensions or smooth morphisms. So we know that cohomology commutes with base change for such things. So that's the reason. So in characteristic P, there's a little subtlety here because it's not true that that extensions of fields are direct limits of smooth morphisms. So inseparable field extensions are not smooth. But the claim is that Etale cohomology is insensitive to inseparable field extensions, and that's something you would prove separately. And okay, so the implicit claim is that if you have like an Etale morphism, it descends uniquely through inseparable field extensions, and that's something you should think about. All right, are there any questions about that? All right. If not, I'm gonna move on to a new topic. So what I want to start talking about now is the Kunneth formula. and cycle class maps. So I think when we finish this topic, I think we'll have maybe just one more topic to go before we can start talking about the actual Weil conjectures. So I think all we'll have left is the Poincare duality and the Lefschetz trace formula. So we're doing pretty well here. Okay, so let me say what the Kunneth formula is. So suppose so here's the theorem, and I'll sketch the proof of this actually. So suppose that X and Y are proper K schemes. Over here, K is algebraically closed. And we'll prove it in a slightly more generality than this, but you really do need some hypotheses. So Kunneth is not true for arbitrary products of varieties. F, well, let me do it this way. Excuse me. So then, yeah, so suppose lambda, well, let's say F is a constructible sheaf on X Etale, G is a constructible sheaf on Y Etale. Okay, then the theorem, and I'm going to state this in a kind of fancy way that we don't quite know how to understand yet, and then I'll tell you some corollaries of it, which are understandable. So the statement is that there's so this is a statement in the derived category, and I'll be explicit about what it means. So if you take the derived global sections of F, and the derived global sections of G, and take the derived tensor product, so those have a natural map to R gamma of X Etale F tensor G. Okay, so and the statement is that this is an isomorphism. Okay, so what are these objects? And what does it mean to have a map like this? And so right now I haven't even told you what the map is. My claim is that there is a canonical map in the derived category. There's not a canonical map. So okay, so what are these things? So this is a complex whose cohomology is the cohomology of X Etale with coefficients in F. One way to write down what it is well, how do you find such a complex? You take an injective resolution of F and you take its global sections. So that's a complex of abelian groups, which computes the cohomology of F. You do the same thing here and the same thing here. Okay, and then, okay, so first now what does this L mean? So this L means you find a quasi-isomorphic complex of flat or projective abelian groups, and then replace one of them with that, and then tensor it with the other. Okay, and then finally, what does this morphism mean? It means that, again, you replace this complex you just got with a quasi-isomorphic complex, and then have a map like this. Okay, and then the claim is that this map is well-defined, or there is a well-defined such map, inducing an isomorphism, and a canonical one, in fact, after you invert all quasi-isomorphisms in the category of chain complexes of abelian groups. So where does this live? So this lives in the category of D, well, really the bounded derived category of abelian groups. Okay, so let me, before explaining where this comes from, let me explain some corollaries. So first of all, there's a special sequence that one gets out of this immediately. So this is what people often call the Kunneth formula, which is, it's as follows. You get the direct sum of, let's see, of I plus j over I plus j equals S of Tor minus R, let's say here lambda, here we have lambda. Let me just well, okay, actually, I think if I put constructible sheaves, I can just put Z here, of excuse me. Sorry, let me actually change this. So here we have a constructible sheaf of Z mod L to the n Z modules. Just to make things a little simpler. So then I can put Z mod L to the n Z here. So we have HI X Etale F against HJ X Y Etale G. And what does this converge to? It converges to HR plus S of X times Y. Sorry, I screwed up the key thing in this statement. So this should be an X times Y here. And this should be a Y. I'm very sorry about that. So this should be a X times Y Etale. F tensor G. So this is X times Y Etale F tensor G. So this is if F or G is a sheaf of flat Z mod L to the n Z modules. Okay, so this vectoral sequence is a little scary, and part of the reason why is that it can be infinite. I mean, these tours, if you take tours of Z mod L to the n Z modules, these things can be non-vanishing and arbitrarily negative degree. Sorry, someone has put a question in chat. Yeah. Oh, thank you, Jose. Sorry about screwing that up earlier. Okay, so what you should think of this as is saying, so the simplest situation is if so suppose F and G are just the constant sheaf Z mod L to the n Z. And suppose, moreover, that the cohomology is free as a Z mod L to the n Z module. Then all of these tours vanish as long as R is at least 1. And then what you get is that the cohomology of the product is the tensor product of the cohomologies. It's a gridded ring. So that's the sort of simple situation here. But things can get really complicated if the cohomology groups are not free. So one corollary of this is that if you with ZL coefficients, things get a lot simpler. So, and that's because the Tor dimension of ZL modules is 1, so you don't get any higher Tors. So then there's a short exact sequence. So this is over ZL. So if you get a short exact sequence, 0 is to the direct sum of R plus S equals M of HR X Etale ZL tensor HS of X Etale ZL. This goes to HM of X times Y Etale with coefficients in ZL, and then the co-kernel is the direct sum for R plus S equals M plus 1 of Tor 1 over ZL with coefficients in HR X Etale ZL comma HS X Etale ZL. So again, in the situation where these groups are free ZL modules, this Tor vanishes, and you just get an isomorphism between this direct sum of tensor products and the cohomology. So just like in topology. Are there any questions about that?
When you go from the statement to the spectral sequence,
Yeah.
in the statement you have like derived tensor product of F and G.
Yeah. Yeah, so that's why I assumed here that F or G had to be a sheaf of flat Z mod L to the n Z.
Oh, okay, I get it. Okay, right.
Yeah, so in general, you would get some hypercohomology here, if not some. Yeah, and then here in this situation, I just assumed F and G were just ZL, so things are a little simpler. Yeah, so let me actually just say a word about where this is coming from, and then we'll say more next time. So these tors are taking the cohomology of this derived tensor product here. So what this is saying is that we have a quasi-isomorphism of complexes. What you do explicitly to see this is you write this down as the cohomology of a double complex, and then this is the so here where you replace this with a, let's say, a projective resolution, then take the tensor product of the complexes, that's the double complex, and then the spectral sequence is one of the spectral sequences associated to a double complex. I would have to write things down and pick either rows or columns first to get that spectral sequence for you. So just a remark, I mean, I've stated the theorem for only for proper schemes, and it's false in general. So maybe let me give you a non-example. So a non-example. So if you take x equals y equals the affine line over K, which is an algebraically closed field of characteristic P bigger than 0, then this Kunneth is false for comparing the cohomology of A1 to the cohomology tensor the cohomology of A1 to the cohomology of A2 in this case, even for H1. Okay, and how would you see that? Well, you can explicitly write down what the H1s are. So there's a little subtlety, which is that I haven't yet told you what this map is. So maybe a priori there could be some abstract isomorphism, but I'll tell you next time what this map is. I think I probably shouldn't start with the remaining 4 minutes. So are there any questions about that maybe in the remaining 4 minutes? So strictly speaking, I did not say derived categories were a prerequisite for this course. So if you're feeling a little worried about them, that's okay. I'll try to be more concrete next time. And I think you should just think of this corollary as the statement if you're uncomfortable with derived categories. Somehow the issue is that I mean, well, this statement a priori has no mention of derived categories, but there's really no clean statement of Kunneth in my view without some kind of derived categories. So maybe just one word. So where does this map come from? So this map comes from cup products. And at least those are not so hard to describe on check cohomology. So let me briefly indicate. So like, what is the map? So I'll kind of give you some piece of the map from HR, X Etale, F, tensor, HS, Y Etale, sorry, G to HR plus S, X times Y Etale, F tensor G. So you can write it down on check cohomology. So remember, there were some assumptions for when check cohomology computed derived functor cohomology. Those assumptions aren't always satisfied, but there is always a cup product actually. So the existence of this kind of cup product is an abstract statement about sheaves of abelian groups on a site. But in check cohomology, we can write it down explicitly. So if we have a cover U to X and V to Y, so then we can write down, so we can represent our element here by some section F on U, and an element here by some section G on V. And then, okay, well now U times V gives you a cover. So now U times V gives you a cover on X of X times Y. So these are covers. And the map on check cohomology is just given by taking F G goes to F tensor G. So it's really not so bad. And then you should convince yourself that that's in the right cohomological degree. So here, this is kind of a concrete description of cup products. All right, with that, we're out of time. So let me stop recording.